And as soon as the link is available, I'm going to make it available to y'all. And then eventually I'll change that from the campus cloud to a more formal YouTube version of this. And it should be indicating that it is recording. So do any of you have questions related to regression homework questions or questions related to regression from last class session? This is where I pause, and in Zoom space, it's always a little bit more awkward than when I'm staring at you in person. Okay, so far, regression, we draw a stinking line through the scatter plot, and the line is to predict the y value from the x value, and it seems to do a pretty good job if the trend is linear. Yeah. And then if a collection of things all hold out to be true, like normality, equality of spread, independence, simple random sampling, or random assignment to different treatment groups, we're in good shape. We could use our method. But last time in the lab, we asked you to check for whether those assumptions, normality, equality, spread, etc., were reasonable. And let's pause for a moment. Any questions coming to mind now related to the lab or lecture from last time? Okay, so it seems like we talked about these things called the residuals. Okay, what the heck is a residual? We seem to treat the residuals almost as if they were the same thing as the underlying true epsilon. So remember our model here, and let's see if I could grab a color to highlight. Yes, I have a highlighting color. Our true model says that yes, there is an average value of y for any given value of x. Literally, if I tell you x and you know beta 1 and you know beta 0, you could plug in and find the typical value of y. Think the typical value of a person's weight based on x, their height. But some people weigh more than others, even at that same height, or other people weigh less than average for their height. So, the part that's circled here, maybe I'll switch over to a different color for highlighting purposes. In pink here, we have our typical value of y for that given x, and some people are not at typical. It's because there's natural person-to-person variability, and epsilon captures that person-to-person variability even within that same height. And that's why the y values, even in a vertical column for the same exact x, aren't all the same. We have a variety of y's, and it seems like these epsilons that we require to be normal, equal spread, and indeed the epsilons should show no trend. The expected value of epsilon is equal to 0 for any particular x. It doesn't matter what the x is. The typical value of epsilon is 0. That's sort of like linearity. Okay. So that's the setup that we've got with the model. Then we have this belief that that we fit a straight line. And a straight line is, you learned in high school, y is mx plus b. I hate in high school in parts. So I'm going to say y is b0 plus b1 times x. I switched the betas, the underlying true Greek letter population characteristic. I switched it to a lowercase Roman letter b to correspond to, well, lowercase Roman things are things that we actually get to know the value of in the data or from the data. So I know all my x's. Yes, I know, yeah, also the y's. The rest of that first equation, I do not know those terms. I don't know beta 0, don't know beta 1, don't know epsilon. But from the data, we get regression estimates B0 and B1. So from the data, I can get those two terms. Yeah, I don't know them in general, but from any given data set, there will be an intercept for that data set and a slope for that data set. So it's in lowercase Roman. And if I tell you B0 and B1 and then X, you construct from that a fitted value, a predicted value, if you will, the Y value that we expect to see from that X. So based on a large data set, 50, 20, 500, 5,000 data points, you literally would get an intercept and a slope. And then from any given X, you get a Y hat that corresponds to the value for Y, the predicted weight you would expect a person would be based on their height, and then the rest of the whole data set. Well, let's do a little bit of extra work and say we want to construct this thing called a residual. Literally, if I take the first equation, if you will, truth, and from it subtract your fitted values for the truth, the first minus second, y minus y hat. I'm just taking that first line minus the second line, and we have the truth. And then we have the fitted version of a trend line, okay? And if I now collect like terms, things with x's all together, things with epsilons all together, and things with neither an x nor an epsilon together, we have beta 0 minus b0, and that should be close to 0, because if our data set is largish in size, our sample slope, our sample intercept should be close to the population intercept. Okay. Furthermore, okay, our our sample slope and our actual slope should be close together. And let's make sure I can underline them together. That should also be approximately 0. And so if you got these first two terms approximately zeroing out, you'd say that the residual, EI, is approximately equal to, well, just the epsilon. So the degree to which the underlying the epsilons are normal, the residuals should be normal. The degree to which the epsilons should have equal spread, the residuals should have equal spread. The degree to which the epsilons should show no trend at all, the residuals should show no trend. So we investigate these residuals because we believe things about the underlying epsilons themselves. So that was the nature of the portion of the lab where we say, now you investigate the residuals to see if the model is reasonable. I will pause now in case y'all have questions related to the lab or doing that. Now, it could be that one of you is raising your hand inside Zoom and I'm not seeing it, because that will happen from time to time, but just unmute. Okay, so I'm in good shape there. Okay, so we have our residuals, and we check those, and like we saw last time, well, I'm not even going to bother doing the example because you already did a lab on this. But for normality, you're going to go ahead and, for normality, you're going to sort of investigate the residuals with a quantile plot, which I like. And then ultimately, if you want to do a hypothesis test for normality, Shapiro-Wilks allows you to tackle with the null hypothesis being normal. It allows you to check, are my residuals lacking in normality? In that same sense, we also want to check for other things. Excuse me. Maybe I'll just show you an example of that one because there's a little bit of a distinction between the first and then the second. Let's maybe eliminate that. In fact, just eliminate all of those. So what's a good data set? Yeah, well, let's try the building heights and stories. So we had that from last time. Okay. Hold on. There we go. Okay. There. Come on. Double clicked. And it is opening. like before, we're going to do our analyze fit y by x. If the height of the building we predict would be dependent on the number of floors. We see a trend line that we could then draw in, fit line. And with that fitted line, with the linear fit, we could choose to save those residuals. Okay, so I chose to save the residuals here, no problem. And I'm going to just investigate in one way the distribution of those residuals because we said they should be normal. Do we have normality? Well, I don't like this vertical formatting. I just like to stack it up because it looks better to me. You do you. I turn on that normal quantile plot and graphically straight line, pretty close. It does look as though it's maybe a little sort of S-shaped, a little bit sort of S-shaped. Is it horribly bad? This graph doesn't say horribly bad to me, but I'm a little worried because we're sort of like, well, close to the boundary, and we're close to this other boundary here, so it looks maybe a little shit. Here's the situation where I'm thinking maybe this is a little bit long-tailed. How do I know long-tailed from this sort of an S shape? It seems as though compared to the straight trend line that's shown in red, we stretch out further to the right and then further to the left. Skewness would be sort of a C shape like that, or this shape. Okay? So we stretch it a little bit further to the left of the lowest values and a little further to the highest values. To formally check for that, I'm going to go ahead and add a continuous fit normal curve. And over off to the very right, I'm going to add that goodness to fit. And I have, borderline Shapiro-Wilk. Well, no, Anderson-Darling borderline p-value, but for Shapiro-Wilk, there's not evidence here of a lack of normality. Comparing to the belief of normal, we have no reason to doubt normality just yet. Any questions about that? Do want to note in this normal quantile plot here, sometimes we talk about linearity in the quantile plot. Let's clear that up just a hair. In the quantile plot, linearity means one thing. Linearity in the graph of the residuals against the x's means a different entirely. Let's again create our fit y by x. We had originally the number of floors. X predicts the height of the building Y. Click OK. If I wanted to draw that trend line in, it's easy to indeed draw it in. I'm going to go ahead and fit that line. Good. And so I see the residuals are here. If I'm sorry, I see the XY trend, XY. If I want to plot the residuals along the y-axis, that's an easy thing to do. This time, instead of Graph Builder, I'm going to choose to use fit y by x for a reason. I'm going to say, let's try the residuals in the y slot and the height of the number of floors the building has. Keep the same x, use residuals in place of y. Let's say I drag it over here to the right. And now I'm going to go ahead and add that fit line. And I'm spotting here the same graph. Remember how we earlier today, yesterday. No, not even yesterday. On, what day was it? Tuesday. We talked about how there was this sort of parallelogram, yeah? That parallelogram is now tied to our new graph. So here are the 1, 2, 3, 4 corners of that new graph. It's almost as though I took my parallelogram, yeah, and said I'm going to pull down on the right side and push up on the left side. And with the pulling down on the one side and pushing up on the other side, where within any vertical column, we have the exact same location. You could call it a shearing forces applied to a collection of things that are all in a vertical slip plate. So this data point, this residual is there. This second residual from the left, right there. 1, 2, 3, 1, 2, 3. It seems as though we have 4, 5, and then a 6, 4, 5, and then 6. There's these 3 over here, and it being these 3 down here, and then at the bottom end, those 3 are these 3 there. So I see the same figure here. The benefit of this second graph, the graph of residuals, is that we can see more easily things like curvature. If there was slight curvature in our original graph, now we didn't see it there. Once we've taken your sort of parallelogram and stretched it out, we would see the curvature more dramatically. So I'm able to see more easily a lack of linearity in the graph of residuals against the x's. I'm graphing the residuals against, in this case, x. You could also graph them against y hat because y hat is a linear function of x. It really would show you the same picture. I just like to go against x because of the parallel nature of how we see stories along the original x and revised x axis. Okay, any questions about the residual graph here? Okay, so we claim we should have equality of spread and we should have linearity. I don't see any lack of linearity here. I can check it though in an easy way. If I use fit y by x, I could say, well, what if we fit a curve? If instead of fitting linear, what if I chose to fit a polynomial like a quadratic? Would the best fitting green quadratic be clearly better than what I have so far with my red trend line? If I'm looking here and saying green, is that clearly noticeably better than red? I'm saying I don't see it. So I don't need that quadratic fit. So under the fit polynomial, I'm just going to go ahead and remove it. I could remove fit. Where is it? There we go. I'm going to stick with the red one, linear. So equality of spread, we haven't checked that yet. We checked linearity. I see no curvature here in the graph of residuals against the x. What about equality of spread? The equality of spread assumption boils down to, well, for the lowest x's, what is the typical range of the y's? For the medium x's, what is the typical range of the y's? For the highest x's, what is the typical range of the y's? Are they all the same? Here, it looks absolutely fine to me. However, if I were seeing a problem, okay, it would maybe be the case that for large x's, we see a much wider y range than for small x's. If there was a lack of equality of spread, I would see the problem there. And here, I don't see that problem. So we've talked through checking the residuals. And as we found, sometimes taking a transformation of the y variable or of the x variable will be helpful creating something that is closer to linearity. Let's show you a different example. Wine disease and heart mortality. Wine and heart disease mortality. So I think it's called W for wine consumption. Move it over here so I can see it. Okay. Looking for the W. There's who you go. Wine consumption and heart disease. Wine and heart disease. Huh. So it looks as though my mouse wants to move. Okay. I can close that. There we go. Okay. Are we doing this? Okay. Wine and heart disease. That is not working for me. And rather than figure that out, I'm going to go right into Windows. Hmm. What is the GMP window that I want? I'm just going to open a file. Okay, W for wine consumption, and that's not even sorted alphabetically. There we go. Okay, so with this wine consumption and heart disease data from I think 1984 or so, A collection of different countries here. We have them is where a lot of white people live. The wine consumption in liters per adult per year, and no, that is not a typo. 2 bottles of wine per week per Italian adult. Same thing for the French. Heart disease death rate, so that's death rate from anything related to heart disease. If I were making a scatter plot or a graph builder, I guess, for making a graph, you'd think mortality may depend on the amount of wine consumption. It seems curved to me. Indeed, we could maybe solve the problem. If you see clear curvature, like I do here, you might want to assess how could I solve that curvature problem. We're going to really focus on that in a later class session, but I do want to suggest something, and that is, what if along the x-axis we have, instead of, let's go ahead and do that. What if we want to, on the x-axis, use change the scale up? And I don't think I wanted to do what I did. Let's redo this. So graph builder. And we had the mortality along the y-axis. X had the slide. And then along the x-axis, if you click your way into it and right-click there for axis settings, notice that it's a linear setting. And those of you who are in engineering might remember log paper. Remember the logarithmic scale that we have? And if this was in a physical classroom, I'd look around the room. On that log paper, we said the numbers, 3 to 4, 4 to 5, 5 to 6, 6 to 7. The scale is different. If it was a linear paper, it would look the same. But I'm spotting from 30 to 40, the same distance exactly as 3 to 4, or 4 to 5 has the same distance as 40 to 50, or 8 to 9, 80 to 90. That is the same physical distance on my graph paper. I'm just adjusting the x-axis. And when I've adjusted this x-axis to be on this logarithmic scale, if I say straight line, you'd say a straight line works. A straight line here describes the relationship between wine consumption and heart disease death rate. So the log of wine consumption is perhaps a good linear predictor of heart disease death rate. How would I pull that off inside the data like you in your lab last time? And maybe I want the other data, not these data. I'm going to create a new column, and I'm going to go with the log 10 of the wine consumption. Now, why log 10? It wouldn't matter if I used a natural log or log base 10. I just like to go with log base 10 of things that I am familiar with being scalable in the log base 10 fashion. Natural log is more mathematically comfortable for a lot of mathematicians, but depending on the context, there might be a natural way that people do it, and just go with what other people in your discipline do. It's all good. So I'm going to go with log base 10. What is the formula? Well, the log base 10 of wine consumption, log base 10 is a transcendental function, log base 10 of what? Of the wine consumption. So log 10 wine should be the log base 10 of the wine consumption. Click OK. And I've got a new column, and I can't do it perfectly, but if I found a country with a wine consumption of about 10, and so between Australia and Belgium, we have close to 10. Log base 10 of 10 is about 1, so a little bit below 1, a little bit above 1. Yeah, that tracks. And 75 is pretty close to 100, so we'd expect the log base 10 here would be 2. If I are creating a graph of the mortality plotted against the log base 10 of wine consumption, we would have approximate linearity, and fitting a trend line would allow me to be comfortable with at least the assumption of linearity. Just a note for this data set, we also check out the normality and the equality of spread. It does look as though there's maybe a little bit wider spread for the low log base 10 wine consumption than for the higher log base 10 wine consumption, but that's because there's so many more countries down here. Any formal check of the equality of spread, we think equality spread is reasonable to believe. And so the p-value down here for is there a relationship, or the p-value for the slope, I feel comfortable saying, yeah, slope is noticeably non-zero. Any questions about that example? Okay. So I'd like to get back into, well, we did the T statistic to test the slope. What about a confidence interval? If you tell me, oh yeah, there's a slope that's non-zero, like we had with the building heights and stories, is let's pull that data set up again, redo our analysis, fit y by x, that the height of a building. Does it depend linearly on the number of floors? Fit that trend line. We check the assumptions. We're all good. Check, check, check. There is a noticeably significant relationship. Indeed, the estimate divided through by the standard error gives me a t ratio, which is highly statistically significant. We see there is a relationship between there is a non-zero slope relating the number of floors a building has and then the height of the building among buildings called skyscrapers. Excuse me. So, because we rejected the null hypothesis that there is no slope, we want to ask, what is that slope? There's information in our estimated slope and then the standard error that allows us to derive a confidence interval for the population slope. Indeed, our sample slope, if you will, your estimate of the unknown population truth, B1 estimates beta 1, B1 plus or minus a margin of error. The margin of error has two chunks to it. One is how certain you want to be of being right. I always want to go with 95% confidence. The reason? Because that's what everyone does. If you walk into a room and say, I've just calculated a 99% confidence interval, or I've just calculated a 90% confidence interval, people will look at you in such a way that you feel the need to justify your choice of confidence level because everyone uses the 95. 95% confidence balances out sort of nicely the width of the confidence interval with how certain you want to be of being right. If you want to be less than 90% certain of being right, you can narrow your confidence interval, which is good, but you have a lower rate of success. Or if you want to be with a 99% level of confidence, again, that's fine for you, but it's going to give you a wider confidence interval than statisticians and the folks that we work with on a regular basis over the years have developed a 95% base level, typical level of confidence, okay, which is going to give you a t value, which is based on n minus 2 degrees of freedom, but I just usually use two if the software isn't going to give me a value for large values of n. Okay, using plus or minus two standard errors gets me in the ballpark quickly because I can always double a standard error very easily. In our case here, you would say our confidence interval is going to be, and maybe I'll move this up so we can see it more easily. It's going to be 11.3 plus or minus twice the standard error, which is 0.5. Twice 0.5 is 1. So 10.3 to 12.3 extra feet in terms of the height of the building per extra floor that the building has. For each extra floor, we have 10.3 to 12.3 extra feet on average. That's what the slope is telling me, and I can estimate that with a margin of error. Something that I found out about 2 years ago that I hadn't known before, and that's sort of cool, is if you click down, right click into the numbers in your table, and I'm right clicking, you can say, what columns do I want? And literally, I could display the lower, right clicking yet again under columns, and the upper confidence interval. So I said 10.3 to 12.3. You could get for free the lower and the upper confidence interval by, again, right clicking and saying, which columns do I want to display? Yeah, usually you get what thing is it? Well, it's the number of floors. Your slope, well, your estimate of the slope, that's the number. The standard error, the t ratio, all for free. The p value, again, for free. Lower and upper confidence interval. Yeah, we indeed might very well want to display those as well. So you could just turn those on if you don't want to do the plus or minus two standard errors in your brain. Okay, questions on that? Confidence interval. Well, I'm waiting for a question. I'm just going to comment that I'm not a huge fan of Zoom from the point of view of questions from students are fewer in Zoom than if we we're in person and I was staring at you one by one. So I've paused long enough for questions. Okay, I'm going to move on then. Okay, let's talk about statistical significance. That's a tough one. I'll just say, is the relationship statistically significant or not? Oh, that sounds like a hypothesis test. Is there a relationship or not? Statistical significance only is related to, do we see a trend? Is the data showing a trend in a clear and evident fashion? Is the p-value below some arbitrary cutoff, alpha 0.05? Okay. Practical significance refers to whether the relationship is strong in a sense of you would care. If indeed I talk to people in construction management and I said, oh, my confidence interval for the number of feet per floor in skyscrapers, if I said, and that was 15, they would say, what? Because that would be so far away from the 10 or so feet per floor that they would expect to see. So tell me about the slope. Is a confidence interval for the slope entirely at a range where you think that matters to me? That is something I didn't expect to see. That is surprising to me as a scientist. That is revealing something of note to me. Okay. So practical and statistical significance, different things. Now, if you have both statistical and practical significance, publish that thing. If you have statistical significance without practical significance, how could that ever happen? Large data set sizes. If you give me enough data, says Archimedes, I can move the planet. No, that was the lever. If you give me enough data, says the statistician, I can find statistical significance. But that doesn't mean anyone would care. I suggested to class sessions back that in a study of all the M's versus F's in terms of incoming student blood pressure, systolic, that's the higher number, the first number in blood pressure, you like 110 over 80, it'd be the 110. There's a statistically significant difference in the male blood pressures, the female blood pressures, and the difference is about 1 or 2 systolic blood pressure points, milligrams of mercury. And if I told you the systolic blood pressure is statistically higher in males than females, you'd say, "Oh, we're concerned. We would want to know more." If I say, and it was 1 point, you'd say, "Yeah, no one cares." Would a doctor care? Would the difference in blood pressure be enough that you'd say, "Ah, that matters to me as a practitioner in the area"? So statistical significance, check. Practical, no. Well, you've just discovered something you just don't care about. Or flip that on its head, statistical significance without practical significance. That's a relationship which, if true, would be important, but you don't even know if it's true. Classic example of that is a small scale agricultural experiment. You're comparing these two different varieties of cucumbers. What you want to do is juice cucumbers for, I don't know, some new health trend, and the cucumber juice, you sort of are going to get more liters of juice per hectare, yeah. And you do 2 plots with the one cucumber and 2 plots with the other cucumber, and you see there's a huge difference, but it's not a noticeable difference. You'd say, oh, we can double our yield if we go with cucumber A versus cucumber B. Doubling is huge. I would care if that were true. Do I know that it's true? No, I don't. Practical significance without statistical significance says just go get a larger sample size. And if you have neither statistical nor practical significance, I guess a confidence interval may be helpful. And you could say within the range of plausibility, within the range of the slopes that are plausible within the confidence interval, are there any slopes that would be of practical significance to a person in your discipline? If so, maybe doing another study to follow up would be important. If it's an important discussion, if it's an issue that's good to sort of pursue. Okay, let's talk about unusual data points. And there are 3 ways that we try to describe whether a data point is unusual. And let's talk about the 3 different ways. And I'm going to maybe start with those high leverage data points. And damn it. I'm going to draw 3 separate graphs down here in the lower right corner. Okay. And For high leverage, I'm going to say, well, if the bulk of your data points are in that range of X values, anything dramatically outside that range is going to be high leverage. Notice that its X value is well above the average X value. High leverage. Okay, so we got high leverage right here. Yes, check. High leverage. However, this one has a residual which is not far from the trend line, which would correspond to the bulk of the data points. Okay, so here is a low residual, high leverage data point. However, let's go with removing another couple of the recent. Do, 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 do. What if we had a data point over here? Again, the bulk of the data points would fit a trend line, but this one is both high leverage and it's a large residual. It's sort of far away from then the average. This is a data point which is influential, if you will. Okay, so far away from the trend line, if that data point were removed, is a way we would say essentially that is a influential data point, high leverage and large residual. Influential data points are worth noting. If indeed you have that data point in your data set, it really is different than if you don't. Now I'm going to sort of look into the lab because there's a question that I think, if not in the lab, I want to use that data set to describe it right now. And yes, we have it in the lab, so I don't have to worry about that. Okay, cool. So these unusual data points, let's just note where they are. And indeed, we might try to fix them. And if indeed you have a typographical error, I was once looking at a data set and I saw 3,200 pounds as the weight of a person in the data set. I said, that cannot be. And so we looked into it, and someone, when typing in the values, literally didn't hit the dot. It didn't hit the decimal mark. And so the software interpreted that as 3200 rather than the 20.0. Certainly removing that data point or fixing it by saying we'll make an assumption that that 3,200 was really 320. Those are two reasonable ways to approach the problem. Another approach, though, that we could take is if you are not able to say, I know what happened, I can fix it. And if you're not willing to just remove that data point because it is a data value. There's a whole fleet of statistical methods that are called robust statistical methods. They're robust against departures from normality and equality of spread. And so we don't really mind having a data set that fits certain one of those assumptions, like the equality of, I guess, normality is one of them. If I used a robust statistical method, even if the distribution of the errors around the trend line wasn't perfectly normal, I'd be okay. I can handle outliers more easily. Again, when you are doing your own data analyses, you're going to say, I got it, got it, got it. Oh, hold on, there's a problem. I want you to be able to, at the end of this class, say, I know what the problem is. I know how to describe it. So I now can go talk to a statistician and say, what do you recommend I do to help solve this problem? Any questions about unusual data points? Okay. So let's talk about two additional questions. Let's maybe go with I'll talk about regression for estimation of the average Y, and I'm not going to stress regression for the sake of prediction, but I'll introduce you to the idea, but not in great detail. Okay. So sometimes if we have an XY relationship, if I tell you Y is typically about B0 plus B1 times X, if I tell you that a building height is 90 feet plus then 11.3 feet per floor, you're saying, oh, well, I could tell you what height I would predict for the average height of a building if the number of floors were 50, or if the number of floors were 62, or if the number of floors were 75. I could tell you for any given number of floors what the predicted height of the building would be. That's easy. But that sounds like a question where I tell you a number, like, hey, what is the average height of a building with 90 floors? Well, that's a question which is answered with a number, maybe an estimate with a margin of error, if you will, a confidence interval would be the approach. So let's talk about uh, my neighbor across the street, David. He is 5'4". What's the average height of all adult males? His height. Okay, we could tackle that question. And then what height would you predict he individually would be? Oh, tougher question. Why? Because you don't know if he's okay. I told you earlier this term he was actually pretty skinny. But if I didn't tell you whether David was skinny or heavy for his height, you just say he's short. And if you gave me a height weight relationship, I could predict the average weight for someone of David's height, but that's estimating the average for someone of that height, 5'4". And if I told you your job is to predict David's individual weight, you go plus or minus wider because he might be heavier than average for someone of his height or much lighter than average for someone of his height. So two different questions where the estimate might be the same. Literally, if I want to know the average value of y for a given x, and I'm going to note that with a mu for average, with a subscript mu nu, it looks like a v, but it's a nu. Mu nu is the average value of y when we know the x value is x nu, a particular value of x. So basically, think of a height. For that height, if you knew the true interception slope, you would have a typical weight for someone of that height. Mu nu is that typical weight. How do we estimate that unknown value? Well, it's not too difficult because we know the actual value. We have an intercept and a slope. We have an estimate of that average weight for someone of that height. Check. Mu nu plus or minus what? Well, the margin of error should correspond to the standard error for mu nu. Again, think standard error. What is the standard error? Standard error tells me the estimate of how far my estimate is away from the number I'm trying to estimate. By the way, was that really loud when I did this? Accidentally. So I think the microphone is in these headphones somewhere. So if it wasn't, actually, I'm going to try it again and see if it's really bad. Oh, that's okay. Okay, so hopefully it wasn't too bad. The standard error of a number, an estimate, literally is an estimate of how far away our estimate is likely to be away from the number we're trying to estimate. Okay? So that standard error, it has some components, and if you want to know why, if you want to know, okay, why does this equation here make sense? It takes stat 524 in some future term. It goes over, hold on, we're not going to have that class in future term. Take what is called stat 524 now, once we convert it to the semester version of the class, and we do a proof of this equation. Right now, I want to highlight three different parts of it. And one part is really pretty easy, and that is n and nn. What if n were in this equation? Okay. N is in the equation. That means more data, more precision, and n is in the denominator of the part inside the root. So n's always within a root, and it's always in the denominator. So the larger the sample size is, the more skyscrapers we have in our data set, the more precisely we know the average value of height of any given skyscrapers based on the number of floors. Okay, so we get more precision for the average y for a given x if n goes up. That probably won't have any questions. Let's try the second part. S sub e. S sub e, what is that? S sub e is equal to the root of MSE. Sometimes it's called RMSE in the regression output. It tells you how close your predictions are to the actual value that you will be observing. Oh, hold on, that makes a lot of sense. How close are my predicted values to the ones that will be eventually observed. S of E tells me a measure of spread of data around the trend line vertically. Vertical spread around the trend line is what S of E measures. And if there's more spread around the trend line vertically, then we're going to be less precisely knowing the average. But if we have little spread around the trend line, like with the building's heights and floors, we're going to know very precisely the average value of y for any given x. There's one last term here, and that is that third thing, and it's literally what x are we talking to compared to the average x and the standard deviation of the x's. Inside this root, we have the deviation of this x from the average x expressed in number of standard deviations of the x variable. So think small values here. Once I've got the whole thing, if it's less than 0.5 or less than 0.1, if I square it, it's going to be infinitesimal or tiny, tiny, tiny. If x minus x bar over sx, if that's like a 2, if I square it, I get a 4. It balloonifies. That is not a word, but it should be. Balloonification should be a thing you know. Squaring numbers that are less than 1 makes them smaller. Squaring numbers that are a lot less than 1 makes them a lot smaller. If it's more than 1, it makes it bigger. So basically think tiny values inside the parentheses. We don't care. X's that are close to the average X end up with little variability, okay, in our estimate of the average y for that x. So if we're talking about an x close to average, we very precisely know the truth. For x is far from average, we don't so precisely know the true average. That's something that GMP can display quite nicely. Notice within that linear fit, if we click on this thing, we could notice how I, excuse me, I could shade in a range of values for the confidence interval. So confid shaded fit. I'm shading in here is a range where, depending on the x, we believe the average y is likely to be. Okay. If I want to sort of highlight that, confid individual limit formula, that should give me 2 new columns, literally the lower and the upper value. So if you give me an X value like 40, I could look and find something that was 40 floors and say I'm 95% sure that I'm sorry, I apologize. I did the wrong thing. Delete that. Okay, that. No, I can't delete that. Okay, so I apologize. I did the wrong thing. What I wanted to have shown you is not for the individual, but for the mean, mean confidence limit formula. There we go. That's better. So for that 40 floor building, okay, again, 40 floors, we re-highlight that for the 40 floor building, ignoring that, which was a mess. I'm going to say the average value for Y is in this lower to upper confidence interval for the mean y for that x. So it's 527 to 557 feet. I'm going to say at 40 floors, we're going 527 to 557. That's a range of values, which is pretty narrow. I think if I were to zoom out, and then let's make it wider so I can see only the 40 there. We're saying if x is 40, the average y is 527 to 557. This equation, once implemented for an x of 40, compared to its x bar divided by the standard deviation, we're home free. But what we can spot is also for values of x that are not close to the average x. Let's look at our graph again. X's that are not near the average x. Let's maybe go down and look at all of them again. We're building with 100 square feet. 100 floors, I apologize. Notice that we have is a wider range of possible Y values. Then if X is 40, it's a very narrow range. For a building that's extrapolating to a very large number of floors compared to the data set that we have, if we're extrapolating, even if the slope is off by a tiny bit, that causes a lot of error in the average Y because we're far from the fulcrum. The fulcrum being the average X, we're going to, for X's that are far from average, we're going to have less precision in Y. So the further you are away from the average X, the more likely you have the X minus X bar squared being really sizable and thus impacting your measure of spread for the average Y for that given X. Okay, any questions about that so far? Okay, so it being just afternoon, I'm going to say the confidence interval, that's easy to do. Your predicted value of Y, your estimate of the average Y for a given X new, plus or minus 2, well, times the standard error. Yeah, you're home free. You're home free because it has only to do with N, X bar, SX, and X new, the new X that you plug in. So these are numbers that you could pull off with a by hand calculation. That is it, other than one last thing. I'm going to skip over the prediction interval for Y new, because that's something in this class which is rarely needed by students. I'm going to say that R squared, the value of R, once you square it, is commonly provided to y'all. You might have noticed every time we've done a regression in the past, it seems to, in our summary and fit, tell you not just RMSE, root mean square error, okay, also tells you R squared, 0.9035555. How do I interpret that 0.90? I'm going to tell you that R squared, which, yeah, literally you could calculate based on SS error and the sum of squared differences from the average value of Y, sometimes called the coefficient of determination, but not often. Depends on the discipline you're in, whether you'll hear the term coefficient of determination or not. R squared measures the variance in the residuals versus the variance in Y. Okay, that's our 1 minus part. So 1 minus what is unexplainable is the proportion that we can consider explained. So SS error over SSY is the proportion of SSY that is not explained. R squared is the proportion of variability in Y that is explained. So we want to sort of close out by saying what values of R squared are good. And I'm saying it doesn't depend just on the discipline, but also the nature of the problem in your discipline, and then also how the data are collected. Oh my gosh, that's a lot of things. I'm just saying until you get really familiar with R squared, don't read too much into it by thinking, oh, that's good or oh, that's bad. I've bumped into folks in some disciplines where they get an R squared of 0.995 and they're bummed because they're only able to explain 99.5% of the variability. And why? Because they want it closer to 100%. Because in their discipline, typically it's almost always exactly 0.9999. And they were so far away from that. So in R squared of 0.995, I think for most disciplines would be considered unusually good. I've seen an R squared of 0.12 before, and the guy that got the 0.12 because it was in sociology, they were ecstatic that they were able to explain even 12% of the variability of Y based on their X variable. So it varies widely from field to field, and then even within portions of the field. So I'm going to say don't read too much into it. R squared will probably not be all that helpful. Just think larger R squared for the same data set is sort of a better fit, and we'll fine tune that later. Okay. Um, I sort of want to close it out now, being respectful of your time, because you all have a lab that you're going to deal with. So, for those of you who are working, intended last time to sort of work in this Zoom space, stay on. For those of you who are going to do your work elsewhere, that's fine too. Drop off. But anyone who's left, I will put you in a Zoom room. Or if it's like, I don't know, you tell me. Do you want me to create 2 or 3 Zoom rooms, or Are y'all good, or what do you want? I'm here. I'm happy. You are too. Tell me what you want me to do. So, Kevin and Kara, you are not telling me now what you want me to do. June Chang, you are not yet telling me what you want me to do. Were the three of you in one group together?
I don't think either of my group mates are here, so I'll probably drop off.
Sure, sure. Okay.
Yeah, I was gonna do the same.
Okay,
Thank
sounds
you so
good.
much.
Yeah, we'll talk to you soon. Bye bye.
Thank
Bye.
you.